November 18, 1987. It is a standard evening at King's Cross, one of the busiest underground transit hubs in London. Deep below the city streets, thousands of commuters are packed tightly together, making their way to the surface on a series of steep, wooden escalators. Halfway up these shafts, a passenger spots a faint glow coming from beneath the steps. It is a small, seemingly isolated fire. When the London Fire Brigade arrives 10 minutes later, they treat it as a routine incident. But within seconds, the situation escapes all control. A massive jet of flames suddenly shoots upward, tearing through the escalator shaft and violently engulfing the ticket hall above. In the end, 31 people lose their lives. A minor spark had escalated into a catastrophe with no obvious physical cause. This severe disproportion between a small, contained fire and a lethal explosion pushed investigators into a 7-month search for answers, challenging their basic understanding of how fire behaves. This visualization demonstrates the foundation of fire investigation: thermodynamics. Heat rises. When an object burns against a wall, the rising heat creates a distinct V shape that widens as it moves upward. If the source sits slightly further out, it forms a U-shaped pattern. By measuring the depth of the charred carbon left behind on surfaces, investigators can trace the path of destruction in reverse. The thickest char points to where the heat lingered the longest. These patterns become complicated if the flames are pulled horizontally toward fresh oxygen sources, like open doors or broken windows, shifting the visual evidence away from the actual origin point. The evidence at King's Cross, however, defied all of these principles. Multiple eyewitnesses reported that the flames did not burn upward toward the ceiling. Instead, they burned at an angle, laying perfectly flat against the horizontal slope of the steps. The physical evidence directly contradicted the basic laws of thermodynamics. To trace the origin of the disaster, the investigation team had to discard standard forensic models and start completely from scratch. The first priority was to check for deliberate interference, but when specially trained dogs swept the station, they found zero trace of chemical accelerants or gasoline. Attention then turned to the mechanics of the escalators themselves. Beneath the wooden steps, investigators found thick layers of heavy grease, packed with dust, fibers, and dropped debris that had accumulated over years of operation. Test runs on open models proved that a discarded match easily ignited this mixture. Yet the physical models showed that the flames would only burn vertically and quickly extinguish themselves. Another theory suggested that the dense 20-layer sex paint on the ceiling above the escalator had absorbed the heat, ignited, and rapidly carried the fire up the shaft. Witness accounts dismantled this idea completely. Survivors explicitly stated that the flames never touched the ceiling at any point during the initial fire. With every physical theory exhausted and the rules of thermodynamics seemingly suspended, investigators realized traditional observation was no longer sufficient to solve the problem. They turned to the highest level of computational power available in the UK, the Cray 2 supercomputer, typically reserved for highly complex scientific modeling. Researchers fed the exact geometry of the station into the machine, asking it to calculate the fluid dynamics, temperature gradients, and gas flow within the escalator shaft. Looking at this cross-section of the simulation, the computer produced a result that matched the eyewitness accounts. It predicted that the fire would ignore upward buoyancy and instead hug the length of the wooden steps. The solid, trench-like side walls of the escalator shaft prevented the flames from spreading horizontally outward. Forced into a confined space, the heat had nowhere to go but up the path of the trench, parallel to the slope. The physical structure of the escalator itself was actively dictating the flow of the fire. As the stream of hot gas accelerated up the incline, its internal pressure dropped, altering the aerodynamics within the shaft. This pressure difference created a suction effect, pulling the flames physically downward until they were pressed flat against the steps, creating the strange horizontal burn witnesses reported. To anyone standing above, it looked like a harmless, contained fire. But trapped tightly beneath the surface, the superheated gases were baking the entire length of the wooden escalator, pushing the internal temperatures well past 500 degrees. This environment was perfectly engineered to trigger a flashover. This occurs when an enclosed space becomes so intensely hot that all combustible materials inside reach their auto-ignition temperature simultaneously, bursting into flame without needing direct contact from a spark. The superheated wood of the long escalator finally crossed that thermal threshold. In a fraction of a second, the entire shaft ignited at once, sending a massive jet of fire rocketing up the tunnel. The aerodynamics of the shaft had hidden the true scale of the heat. By forcing the flames down, the trench camouflaged a rapidly building thermal bomb, leaving the passengers in the ticket hall completely unaware of the energy hurtling toward them. The computer's output was so highly counterintuitive that investigators refused to finalize their report until they constructed a 1/3 scale physical replica of the shaft to test the data in real life. Once lit, the fire in the physical model burned upward for a few minutes before laying down and violently hugging the floor, exactly as the computer had predicted. A previously unrecorded law of fluid dynamics had been confirmed: the trench effect. The findings triggered sweeping changes across transit infrastructure worldwide. Wooden escalators were systematically dismantled, replaced by metal, and heavily outfitted with automated heat detectors and sprinkler systems. By treating physical anomalies as data rather than errors, and pushing early computing to its limits, investigators mapped an invisible force of physics, ensuring that millions of commuters would safely reach the surface every single day.